Boker Tov and good morning to all. Today I need to fulfill the promise that I gave you in the previous video. Namely, if we start with an inner product vector space, then if you define the square root of the product of V by itself, then this is an actual norm. Namely, we need to show that it satisfies the triangle inequality. Okay, so let's start. So as a reminder, we have a vector space V and we have an inner product on V. Namely, it satisfies the three conditions. It is non-negative, Hermitian, and linear in the first variable. And then we define the norm of V to be the square root of the product of V by itself. And we have already seen that it is always non-negative. And also the norm of alpha V is the absolute value of alpha times the norm of V. Right? These are two properties that we expect from any sort of generalization of a length of a vector. And then we want to talk about the triangle inequality. So again, if you want to go from A to B, then the straight line is the fastest route. So this is the triangle inequality. And this is what we want to show. Namely that if you define the norm in this way, then it satisfies that the norm of V plus W is at most the norm of V plus the norm of W. Okay, so let's start. Okay, so as a first step, we just take this new notation and write down whatever it means. So the triangle inequality is equivalent to this new inequality, which is a little bit difficult, right? We have lots and lots of square roots. And in order to get rid of them, we can square both sides. However, we need to be a little bit careful because the fact that a smaller than b is not equivalent to a squared is smaller than b squared, right? This is in general not true. It is true if both a and b are non-negative, which is our case, right? Everything here is non-negative, everything here is a norm of some vector, and we know that this is non-negative. Okay, so let's square both sides. Already the left-hand side is much easier. The right-hand side still needs a little bit of work. So we have both brackets on the left-hand side and on the right-hand side, so we can open it up. And finally, we can cancel some of the terms. We can cancel the inner product of V by itself and the inner product of W by itself. Okay, so all in all, the triangle inequality is equivalent to this inequality. So at this point, I started with the very intuitive geometric triangle inequality and managed to show that it is equivalent to this new inequality. However, I don't really have any sort of intuition about what happens there. So I need to somewhere get a new intuition. Now, the way that I do it, at least one of the ways, is to look for the most simple setting which is not trivial and try to understand it there. And once I do, try to generalize it to the more general case. Okay, so let's clear the board. And I want some test case. And for me, the simplest non-trivial case is the real plane. Right? I can talk about complex numbers, but this is a little bit complicated. So let's stick with the real numbers. And I can talk about the real line, but this is a little bit too trivial. Right? So the simplest setting which is not trivial is the plane. So one of the advantages of working over the real numbers is that the inner product is symmetric. So our inequality from before is equivalent to this one. So 2 times the inner product between V and W is at most 2 times the length of V times the length of W. Right? We are in the real plane. These are actual lengths, not just norms. And now we can cancel the 2 and move stuff around and get that this is our new inequality. The product of V and W divided by the size of V and the size of W should be at most 1. Now we are already familiar with this expression, right? In the plane, this is just a cosine of theta, where theta is the angles between V and W, and we know that cosine of theta is at most 1. So this is great, because we have a little bit of intuition, we know that this is true, and if we can manage to understand it well enough, and somehow maybe to write the proof using only notations of the scalar product, then maybe we can extend this proof to a general inner product space. Okay, so this is our goal right now. So let's put on hold the triangle inequality, and we want to show that in general inner product space, the cosine of theta is at most 1. But again, we don't have actually cosine of theta in general inner product space, but we have this new expression that we think of as the cosine of theta, and this new inequality is called the Cauchy Schwarz inequality. Okay, so we want to understand it first in the standard Euclidean geometry and try to then extend it. Okay, so now we have these two vectors and we have the angle theta between them, and we want to show that cosine of theta is at most 1. And of course, whenever we want to talk about the cosine of some angle, it is better to think about this angle inside a right angle triangle. So let's look on the right angle triangle. And now the cosine of theta is just x divided by z. And to show that it is at most 1, we need to show that x is smaller than z. So why is it true? Why is in the standard Euclidean geometry x is smaller than z? Well, we have this result saying that the hypotenuse in a right angle triangle is always the larger side, so z is larger than x. But again, what is the proof for this claim? Well, the proof basically uses the Pythagorean theorem, which says that if you have x, y, and z, then x squared plus y squared equals z squared. And because y squared is larger than 0, then x squared plus y squared is larger than x squared, so z squared is larger than x squared. And both of x and z are non-negative, which means that z is larger than x. Right? So the fact that the cosine of theta is at most 1 is a direct application of the Pythagorean theorem. Okay, so now we have the proof in the standard Euclidean geometry, and what we want to do is somehow generalize it, write it just using inner products, and hope that this is true in general inner product space. Okay, so before I start, I just want to change a little bit the Cauchy Schwarz inequality, and instead of writing it just the cosine of theta, we write it as follows. So now we don't need to divide by the norm of v and the norm of w. We don't want to divide by 0. And this is a standard Cauchy Schwarz inequality. Okay, so let's start the proof. And again, what I want to do is to take the geometric intuition above me and somehow rewrite it only using inner products, and hope that this proof generalizes to a general inner product vector space. Okay, so basically we just need new notations for our x, y, and z. Okay, the simplest notation is for z. Z needs to be the length of the vector v, and in a general inner product space, instead of length, we just take the norm. Okay, so this is x. The second one is x, and the problem with x is that it is not the norm of w, it is not simple. It should be the norm of this red arrow. So let's give it a name. This is going to be w tilde, and x should be the norm of w tilde. However, how do we build this w tilde? Right, in a general inner product space, what can we say about it? Well, in the standard Euclidean vector space, this is just going to be z times the cosine of theta. But we don't have the cosine of theta in a general inner product space, but we do have this new expression instead of it. Right? We can say, instead of cosine of theta, the inner product of v by w divided by the norm of v and the norm of w. Right? This is just a guess. I still haven't proved anything. I'm just guessing that x should be this expression. Now that we have this guess, because z is going to be the norm of v, we can cancel it and get that x should be the product of v by w divided by the norm of w. Okay, so we have a notation what is z, we have a notation what is x, and now we need a notation for y. So y should be the length of v minus w tilde, the norm of v minus w tilde. And here we actually need the vector w tilde and not just its length. So what is it going to be? Well, we know that its length should be x, and we know that its direction should be the direction of w. But we can't just multiply it by w, we only need the direction of w, which we usually think about as w divided by its length, right? The normalized direction of w. So this is a guess, and if this is the guess, and it should be the product of v by w divided by the norm w squared times w, and then y should be v minus this new vector. So again, up until now, I didn't prove anything. I just guessed what should be the right vectors in a general inner product space. And now we know that if we use the fact that y is larger than 0, then somehow we should prove that the cosine of theta, or the inequality of Cauchy Schwarz, should be true. Okay, so let's see that this actually holds. Okay, so up until now, this was just intuition. somehow to guess where is the starting point, and this is the actual starting point of the proof. We have some vector, we take its norm is always non-negative, and we hope that this leads to the Cauchy Schwarz inequality. Okay, so the norm is going to be again a square root of something, so instead let's look on the square, and let's just open up whatever this means. So this norm square is this awful expression. So we have lots and lots of inner product, and some of them have scalars inside the inner product. So let's take them outside. So some of them just go outside, some of them go with the complex conjugation. And now we try to simplify this expression. So the first one is in the less expression. You notice that we multiply by the inner product of W by itself, which is just the norm squared, so we can cancel it. And also, we have the inner product of V by W in all of these expressions, and we have the inner product of V by W complex conjugation in all of these expressions. Right in the middle one, we have the inner product of W by V, but the Hermitian property tells us that this is the same as the inner product of V by W complex conjugation. Okay, so now that we did all the simplification, you should notice that basically we have the same expression one after the other, right? We have 2 times with minus sign and 1 times with plus sign. So all in all, we just have the norm of V squared minus the absolute value of the product of V by W squared divided by the norm of W squared. Okay, so we did all of this process, all of this computation, and we got to the point that this expression is larger than 0. And now we just need to move stuff around and get that the absolute value of the product of V and W is at most the norm of V, the norm of W, which is exactly the Cauchy Schwarz inequality. Right? We started with some vectors that we got somehow, looked at its norm, it is non-negative, opened some brackets, and got the proof. Now, before I continue, let me rant a little bit about this proof, because at the first time that I saw it, I only saw the computation part of it without any type of intuition, which I somehow needed to later find out by myself. And I really hate this type of proofs, right? Because first of all, it is really hard to reprove them. It means that you somehow need to remember this vector, this V minus the product of V by W divided by the norm of W squared times W. And I'm not sure about you, I don't have this type of memory. But more importantly, as I'm emphasizing again and again and again, one of the more interesting part of inner products is that we can use a lot of intuition, lots of knowledge that we have in the standard Euclidean geometry and transfer it to the general inner product space. And if you don't have this intuition, if you don't have this tool in your toolkit, you're making your life so much more difficult. So my advice to you, if you ever come across this type of proof, whether your teacher gave it to you, your notebook, your book, try to look for this intuition, try to ask your teacher about it, try to go online and look for it, because it will make your life much easier in the long run. Okay, so end of rant, let's go back to the Cauchy Schwarz inequality, and let me give you a few more remarks before going back to the triangle inequality. Okay, so my first remark is what happens if W is 0, because if W is 0, then the norm of W is also 0, and then inside the proof we divide it by 0, which is of course not well defined. However, if W is 0, we don't actually need this proof because Cauchy Schwarz inequality is trivially true, because both the left side is 0, we have the product of V by 0, and the right hand side is 0 because we have the norm of W, which is 0. Okay, so if W is 0, Cauchy Schwarz inequality still holds. For the second remark, the order matters in the definition of y. You need to take the product of V by W and not the product of W by V. And the reason that I mention it is because we will see this type of expressions in the future. And always, or at least almost always, you will see the product of V by W times W as a vector outside. Right? So the second variable and the vector outside will be the same. So this is just a point to remember for the future. Finally, an interesting question that whenever you have an inequality, the question is, when do you have strictly equality? And again, you should start with your geometric intuition, your standard Euclidean geometric intuition. So we have equality in the Cauchy Schwarz inequality if and only if the cosine of theta is 1. And when is the cosine of theta, or in absolute value, is 1? If both vectors are on the same direction or are in opposite directions. Right? If either the cosine is 1 or the cosine is minus 1. And formally, this is exactly when y is 0, so the norm of this vector is 0. And we know that the norm is 0 if and only if the vector is 0. So we have that v and w are the same up to this weird scalar. And you should show that there is a scalar if and only if there is some scalar. So if they are collinear, if v is alpha times w for any type of alpha, then this alpha must be this scalar. So again, Cauchy Schwarz inequality is an actual equality if and only if v and w are collinear. Okay, so now we're done with the Cauchy Schwarz inequality and we want to go back to the triangle inequality. And this is actually very simple. We want to start with this expression and show that it is at most this expression. So we start with the properties of inner products, and the product of w by v and the product of v by w are the same up to complex conjugation. And now we have a number plus its conjugation, complex conjugation, which means that this is 2 times the real part of this number. And the real part of a number is always smaller or equal to the absolute value. And finally, we can use the Cauchy Schwarz inequality and get the triangle inequality. Okay, so this is everything. Okay. Finally, just like with the Cauchy Schwarz inequality, I want to ask, when do we have equality in the triangle inequality? So let's first think in the geometric interpretation, in the standard Euclidean geometry. When do we have a triangle where one side of it equals to the length of the sum of the length of the two other sides? Well, exactly when the triangle is degenerate, right? Everything is on the same line. So basically the two other sides are on the same line and on the same direction. Okay, so what does it mean in a general inner product space? We need that all the inequalities in the line above should be actual equalities. So first of all, the Cauchy inequality should be equality, so v should be alpha times w. And also the real part should be the absolute value. So we write the real part of the inner product of alpha w by w should be the absolute value. Okay, so first of all, let's take alpha outside of the inner product. So we have alpha times the norm of w squared. Now the norm of w squared should be a non-negative number, and you can assume that it is actually positive, because if w is 0, then of course we have equality. So if the norm is positive, we can actually cancel it from both sides and get that the real part of alpha should be the absolute value of alpha. And finally, a complex number which has the real part is the absolute value must be non-negative. Okay, so in other words, we have equality in the triangle inequality if and only if not only v and w are collinear, they are on the same line, they are actually on the same real line, even if we are over the complex vector space, and not only on the same real line, but on the same direction. Right, so this is exactly what we expected from the standard Euclidean geometry. This is still true in general. Okay, so let's summarize a little bit the material so far. We wanted to understand the standard Euclidean geometry and somehow extend it to other places. So we talked about angles or the cosine of the angles, and it led us to the definition of inner products. We talked about lengths, and it led us to the definition of norms. And we managed to show that if you give me any inner product space, then the square root of the product of v by itself is going to be a norm, right? It's going to behave like a length of a vector. Now, in general, in this course, I will mainly talk about norms induced by inner products, right? The type that we see below. However, as I said before in the previous videos, there are other norms which are not induced by inner products, and I do want to talk about them just a little bit more, and this is what we're going to do in the next video. I do want to show you a little bit how to think about these norms and how to visualize them. Okay, so we'll see it in the next video. It is not too important for the rest of the course, but it is something interesting, and I will see you then.